do dimensional analysis. And we're going to get into that over and over again. You will be able to understand what dimensional analysis is all about, okay? Dimensional analysis algebra applied to the unit of measurement, and each new parameter we define has a new unit that is a combination of the major SI units. Okay, so far, what are the major SI units that we have seen so far is the meter for length, the second for time, and the kilogram for the mass. There are more, there are 4 more, right? But let's stick to this one for now. And then when we start defining new quantities, okay, like the primary, like I'll call the secondary definitions, right? We are going to come up with new units of measurements that are going to be a combination of those 3 so far. So what I want to do today is to talk about one-dimensional motion. Okay, that's the science of kinematics. We study motion in physics. Okay, we study motion in physics. And in this course, you see this, you are going to study the simplest type of motion. We will study the simplest types of motion. So you gotta understand those simple type of motion so you can understand the more complex ones that you're going to see in your professional life in the future. Okay, everything that we do here, is just the solid foundation for instance, launching satellites in space, in deep space, launching spacecraft in orbit, around the orbit of the Earth, to the other planets and so on, and other things as well. Okay. So the book did it kind of in a different way. The book treated one-dimensional motion in a more complex way. I don't like the way they treat it. Okay, let's write that down here. The book treated one-dimensional motion in a rather complex way, the way that I don't like it. Okay, the way I don't like it, and which is also the way very few books do. Okay. So let's treat it in the simplest way, and then when we move forward, we start doing the way that the book does, which is he used the vector treatment. We're not going to do that now yet, so you don't have to worry about vectors. Okay. So here we go. Let's recall what we have done so far that I told you, right? We talked about the basic quantities. There are 7 basic quantities. Length and time and mass are 3 of them. You don't have to know about the other 4. We have 2 primary definitions. Position, that's represented by the letter X. It's related to length, but it's not. And then we have force, which are going to see in more detail later on. And laws of physics, we're going to see that later on too. You don't have to worry about them. All you have to know is that there are 3 quantities, three basic building blocks. Don't call it quantities. The right way to mention that would be the 3 basic building blocks. And you have to know the position X, the length, time, and mass. Okay. And we're going to treat one-dimensional motion. I'm going to give you an example of one type of one-dimensional motion. And in order to do that, I have to stop sharing my document. Okay, so here you go. I have this eraser here in my hand. Do you see that, the green eraser? A very simple one-dimensional motion is this one you're going to see right now when I release my eraser. Here you go. Do you see that the eraser moves in just a straight line? This is one type of dimensional motion. One example of one-dimensional motion. I also, sometimes, let's do that again. Here you go. Another type of one-dimensional motion would be in the one direction, okay? In the horizontal direction. Here you go. You can have an object oscillating back and forth to the horizontal direction with a screen, okay? That's one-dimensional motion is all about. When we say one-dimensional motion, we are referring exactly to the x-axis that you learned in the Cartesian coordinate system. Let me get my illustrations here and start sharing that with you. Go. Yeah. Okay, you saw that before, right? You saw something like that before in the last class meeting. I'm going to start sharing the screen again. Share the screen. Here you go. Okay, so what we did before is start, practicing writing those things, right? You should already know how to do the x-axis, something that you have learned in math. Here you go. I'm going to simplify here. That would be my very first slide, right? I like to play this I call it playing the movie. You start with a straight line running in the horizontal direction. I like to put the arrow only at one end of the line. I don't put it on two ends of the line, okay? I put the arrow on one end of the line to indicate that the positions are increasing from the left to the right. Okay, and then what I do next, I put the position, right? And put the unit of position between parentheses. In the next slide, I write down, I put the divisions, right, of my coordinate axis, of my x-axis. In the next one, I labeled the origin and the other values of the position 1, 2, 3, 4, 5, 6, 7, right? And then to the left of the 0 is going to be negative numbers. And if we restrain our particle to move only along this axis, we have one-dimensional motion, right? If this particle move only along this axis, we have one-dimensional motion. However, if the particle is going to move like that, that's no longer one-dimensional motion. It's going to be two-dimensional motion, right? We're not going to treat that yet. It's a little bit more difficult to treat two-dimensional motion and even three-dimensional motion. If you're working, like I said, if you're working for the military, another type of application of motion is the launching of rockets, right? To hit a target, for instance. So before you go ahead and program your rocket to launch, to hit a given target in the distance, you have to learn the basics, the foundation that we are covering here right now. The simplest type of motion, that is one-dimensional motion. In the case of the launch of rockets, the motion can be at least two-dimensional and even three-dimensional motion as well. Okay, so let's say, suppose that I give an instant of time, the particle is at this position, right? So what position would that be? Just a time t equal to 0. Let's put t equal to 0, just like we did before in the previous class. T equal to 0 seconds, the particle is right in here. All right. And then later on, t equal to 0, x, we say that the position of the particle is x equal to, what would that be? I want to ask you that. Think about that on your side. X is going to be equal to minus 3 meters, right? According to this coordinate axis. And then a little bit later on, I want to put this one, I'm going to use this one here. The particle moves to another point along the x-axis. And I'm gonna write that down, not t equal to 0. Here you go. I don't need that. Let me erase this one here. Here you go. T equal to 0, x equal to minus 3. Now, a little bit later, the particle is going to be, I'm going to put the T1, okay? T1 greater than 0 seconds. T1 can be 1 second, 2 seconds, 3 seconds. We in physics and math, we like to work with genetics, right? That's why we write down T1 to make it look nice. Here you go. I'm going to put in italics here. X equal to 3 meters. Now, for the particle moved elsewhere. At time t equal to T1. Okay. Now x is going to be equal to what? You're going to write down 1 meter. To make things simpler, okay, I'm going to put it 1 second later, okay? 1 second later. And later on, we start working with genetics. Okay. So this is just an example of what I'm going to introduce to you right now. I'm going to introduce you a new type of definition. Okay? So let's going back here to my notes. One-dimensional motion, okay? Okay, so remember, one-dimensional motion, we use the primary definition of position. You saw this idea there. And then, you know, we also define something that we call displacement. Remember, displacement is different of position. And there is a specific definition for displacement. Displacement is something that depends on the definition of position. Here's our starting point, right? And then every idea that follows up is going to depend on the ideas that we define on our starting point. So what's the definition of displacement? Displacement is just the final position minus the initial position. That's what we call delta x. Okay. In our example there, our final position was what? Was not 3 meters. Our final position was 1 meter, right? That's the final position. Okay. Our final position was 1 meter. And our initial position was what? Was minus 3 meters. Okay, so let's fix that, right? Minus 3 meters. But let's not forget, you know, it's minus. Note the definition of the delta x, right? Of displacement is the final position minus the initial position. The final position is 1 meter. The initial position is this one right here. Is minus 3 meters. So when we do this math, we are not going to get minus 2 meters. We're going to get plus 4 meters. Okay. So that's our first secondary definition, displacement. We're doing that because we're going to use this definition here for what's going to come next. Okay. Yeah. Let's see, is everybody in there? Yeah, if I sometimes, I get busy lecturing here and I forget to let you folks in. Okay, so let me know if anybody's waiting there in the waiting list. Okay. Okay, so simple enough. So go ahead, store this definition in your head. Right now you have not only the primary definitions, now you also have this secondary definition. That is displacement. What is the unit of displacement? Is the same unit for position. Okay, notice that we are operating, we are summing summing and subtracting the same unit, right? That's very typical here when you're doing physics. You never, note, I'm going to put a note here. Note that we are summing and slash subtracting values that have the same unit. Okay. This value here has the unit of meter. This other value has the unit of meter. Okay. When you sum or subtract quantities, numerical quantities, they must, I'm gonna put here in bold, must have the same units. Remember that, okay? You cannot sum or subtract meters with seconds, or meters with kilograms, or second with kilograms. Do you get the idea? Okay, when you sum and subtract. Okay, notice that a very important rule for operation with units. This is a very important rule for operation with units. Okay, this is a very important rule for operation with units, with numbers. Here you go, with values that have units. Units. Okay. But remember, I put it specifically sum and subtraction. I didn't say anything about division and multiplication. Okay. I didn't say anything about division and multiplication. I said only sum and subtraction. Position is a quantity that can be negative. So it's displacement as well. Okay. It all depends where is going to be the final and initial position. So think about different examples like this one here, right? In which the displacement might be positive, might be negative. Let's see here. Yeah, think about examples like this one here. That displacement might be negative. This displacement here ended up being positive. This displacement here ended up being positive because the particle displaced to the right on this x-axis. Can you see that? I'm going to illustrate that for you again. Here you go. And now I'm going to illustrate with here you go. The initial position of the particle was originally where? Was originally here at -3, right? That's where the particle was originally located at. Between 0 and 1 second. I should put the equal as well. Okay. And we ended up having a positive displacement in this case. And a positive displacement can also be represented by an arrow pointing from the left to the right. Here you go, right here. See that? Initial position here, final position here. So let me give you an example in which, think about an example in which the displacement is going to be negative. Okay? Think of an example in which displacement ends up being negative. I'm going to elaborate a little bit more here. Here you go. I'm going to put here this one, x naught for initial position. Okay. And I'm going to put this one as well, the other one, the t, right? I'm going to put that as a t naught. That's how we represent the initial position and initial instant of time. We usually use the naught there at the bottom, not for representing the zero, right? For the final instant of time and for the final position, just use the x without the subscript there to simplify. Okay, so here you go. What you see writing here is the displacement. I'm going to write it down here. Displacement. Font. Right. Symbol. Good. Now we have what I want. Here go delta x. Get used to this notation. Most books will use that. Okay, delta x. And that's exactly what I have there in my notes. We usually drop this subscript when we write down the final position. Okay, so let me drop that for you. Okay, here you go. I'm going to do the same here. We drop it to save on time when we are solving equations. Okay, so any questions? Is that clear? Okay.
Professor, quick question. I went on your YouTube channel to look for your videos this past week, but I didn't see it on the YouTube channel. So when I want to watch our class recordings, how do I find it?
Yeah. Okay. Did you go to my YouTube channel there? There's a bunch of videos there, right? And you're talking about the video of the first two classes? Is that what you're talking about?
Yes, Professor.
Okay, I didn't upload them yet. Okay, I didn't upload them yet. But the videos that we did, you know, I will upload it. Okay, and I'll let you know. And also, you know, you might want to go through some of those videos because those are old videos that apply to this class as well. Okay, but I'll get that to you. I'll get to upload the videos.
Thank you so much.
Okay. So that's our first secondary definition. Okay. So let's talk about the negative displacement. Have you figured out how to come up with a negative displacement? Okay. One way to come up with a negative displacement is to invert, you know, the positions here of the previous example. Okay, so now, you know, instead of having this one here being the final position, okay, I'm going to make this one here the initial position. Okay, so that's going to be this one 0 seconds, and I'm going to use the notation here, T naught. T naught. No, not this one. Next one. Go. T naught right in here. And the X naught is going to be 1 meter. Okay, another example. This is another example. Okay, and let's see here. No, I don't want to do that. I want to do it this way. Here you go. That now, let's say T equal to 1 second. I'll put 1 second here, right? And then you do the maths, just like before. You're going to get what? Displacement for this other one. Another example, right? Okay, another example for displacement. Displacement. I'm going to get this. I'm going to copy that. XF minus X naught. In this case, XF is going to be, hey, wait a minute. Did I do it right? Yeah, that's right. Minus 3 meters. And X naught is going to be, I'm going to emphasize that's plus 1 meter. And when we do that, now we get a negative displacement. Going back to my illustration, right? Right in here, here you go. I'm going to even copy what I have here. Go. Now my delta X is going to be on the other way, on the other direction. That's no, coincidence that a negative displacement is represented by this arrow pointing to the left. That's no coincidence. Okay. Okay, X, go another example, right? XF, X naught, initial position, final position. Okay, X-axis, initial position, final position. Initial position is 7 meters, final position is 4 meters. In this case, it's going to be centimeter, the different unit. Okay, here you go. That's another displacement. Minus 3 centimeters. Third example. Okay. Another example. From 4 to 7. Initial position 4, final position 7. Let's see here. No, it's all the way around. You go 7 minus 4. Okay. And so on. Okay. So simple enough. Okay, so here you go. Just to emphasize, you cannot sum parameters with different units. You cannot have a summation with a summation or subtraction with between position and time. Okay, that's because they have different units. And that's how our definitions look like so far. The primary definition of position, the secondary definition of displacement. And now we're going to talk about another definition. Okay, is a tertiary definition. Is the definition of average velocity. And how do we define average velocity? Okay, I remember, when I was a little kid here in Brazil, I used to calculate the average velocity of my car when I was traveling with my family from one place to another. Okay, I used to do that. Didn't have anything to do, right? Was inside the car, locked in the car for 4 hours in those long trips, traveling from São Paulo to Rio. And why would I do that? Not because I didn't have anything to do, but I want to also to predict what time I was going to arrive in Rio when we were leaving São Paulo. Sometimes it would work, sometimes it wouldn't work because we'd get traffic along the way, right? Things that we cannot predict. But in many situations, it can be very predictable to find the position of an object in space, especially satellites that are orbiting the Earth, spaceships that are flying away from the Earth into the other planets. Okay, so, and then in order to do that, you need this other definition. Not only need the position, not only need the displacement, you also need the definition of average velocity. Okay, and the definition of average velocity is, the displacement over time. Some books represent the average velocity by this symbol. Other books represent the average velocity by this other syllable. There's a bar there at the top of the letter. Okay? And the definition of average velocity is going to be delta x over delta t. Notice that in this case, we can combine quantities of different units because we are dividing, okay? We are dividing them. You cannot sum those two quantities here because they have units. You cannot subtract them, but you can divide and you can multiply them and create a brand new unit in the process, okay? So let's go for an example. Go. The simplest of all examples that you're going to see here is this one that you see here in the screen. This object is initially at this position, 4 centimeters. Let me move a little bit upwards at time t equal to 0. All right, here you go. I'm going to move a little bit upwards. And then at a later instant of time, at time t equal to 7 seconds, the object is still there at the same position. Okay? So you go ahead, calculate the delta x, you go ahead, calculate the displacement, and you obtain that the displacement is 0 because the particle didn't move anywhere. The object didn't move anywhere. Because the displacement is 0 and the velocity, the average velocity, depends on the displacement, the average velocity is also going to be 0. It goes subscript average. 1, 2, 3. Let's get it, average velocity here. Let me get this in here. Home. Font. Here you go. Subscript. Yeah, now I got what I want. I'm not going to mention this one yet. A little bit too early to talk about this other quantity. So I'm going to delete that for you. Okay. If I'm going to play the movie, right? Like I like to do, here you go. I will do it this way. Here you go. I would start with the particle initially at position 4 centimeters, time t equal to 0. So that's going to be x naught. In the next slide, the particle moves to this other position. Okay, so I will erase this one. It doesn't move, right? Stay at the same instant, stay at the same place at different instant of time. Later on, right? T equal to 0, T equal to 7. And then what do we do next? Next, I calculate my delta x. That's the simplest example you're going to see. I don't like my delta equal capital italicized. I calculate my delta t, final instant of time, initial instant of time, right? Which is 7 seconds. And then we calculate the average velocity. Right in here. The step-by-step approach, here go, right in here. Okay, right in here. Let's play the movie. Here you go. Start with this frame here. Initial position, initial instant of time. Final position, final instant of time. The particle didn't move anywhere. Delta x is equal to 0. Delta t is 7 seconds. Average velocity is going to be 0. And then you can have other types of problems too, right? So here you go. I don't need that anymore. Simplify my video. This one here, and this one I'm gonna come, I'm gonna erase this one as well. Okay, but what about here? Okay, that's another example. Okay, so here you go. Initial instant of time 0, initial position is 4, and now the particle moves to position 7. Okay. Delta x is 3 centimeters. Okay, I didn't put, let's see. Oh yeah, here you go. I put the final instant of time 3 seconds now. So you go ahead, do the math. What do we get for the average velocity? 1 centimeter per second. Okay, so that's the type of problem that you're gonna, simplest problem you're gonna see. Okay, any questions? 9:36. Let's go a few more minutes here. Now, this one here, okay, here you go. Here's the graphical representation of the, this is another graphical representation of the position versus time of my object, okay? So here you go. So let's do, again, a movie, right? Step by step. First, what do you do? You come up, you're gonna plot, what we're doing here, we're plotting x against time, right? Just like we did last time in our lab. Okay, you write down you draw the x-axis, you draw the y-axis, okay? Plot x against position. And then what do we do next? You label the y-axis at x, you label the x-axis as t. And on the top of that, you put at the origin, you write down the origin is 0, 0 both for t and for x. Here it would be initial, it would be position 0, and also would be instant of time 0. Okay, so here you go. You gotta, let me do it better. 1, 2, 3, 4. Let's see, I'm gonna copy that one. Yeah, let's do it this way. 1, 2, 3, 4, 5, 6, 7, right? the divisions. I don't need that yet. I don't need those points yet. Those are the steps that you take to draw your graph. Here you go, got it. Those are the steps you take to draw your graph. And then you're gonna have more here in the horizontal direction as well. One, two, three, four, 5 seconds. And then what do? We plot our initial and final positions on this graph. Right here. Here you go. And what else do you see here? You see that when you connect those 2 points, okay, you end up having a line with a positive slope. Oh, a line with a positive slope, right? Positive slope means angle between 0 and 90 degrees. Okay, rise, we're gonna have a rise of 3 centimeters here in this case. Okay, here you go, rise. And we're also going to have a run of, in this specific case, of 3 centimeters. Here you go. 3 seconds. 3 seconds. In this case, when you take the slope of this example, you get 1 centimeter per second. And the slope of this graph coincides with the average velocity. Let's make it nice here. You go. Got the idea? Okay, so here you go.
Professor?
Yeah.
Just to confirm, I'm pretty sure you just said it, but the slope is the average velocity, correct?
Yeah, the slope in this specific case is the average velocity.
And then for the rise and run, would one of them be the position and the other displacement, or are those just points that we have?
The rise is the displacement, right? Because it's x final minus x initial, right? Let's write it down. Rise is displacement, right? Write it down. I can also write down as delta x. Symbol. Here you go. The run is what? Delta t, right? We don't give any specific name for that. We just say delta t.
It wouldn't be like time or anything. It would just be delta t.
Yeah. Difference in time. You can write that down. Difference in time. Okay. And the slope is gonna be, rise divided by run, right? Those are mathematical concepts, right, that we use in physics. and give it different names depending on this problem, the situation, on the problem that we are using, that we are solving. Here you go. It's gonna be delta x divided by delta t. Not all. Here you go. End up being 1 second, 1 centimeter per second.
Thank you.
Okay. I'm gonna emphasize that a positive quantity. Delta x can be positive and negative, but delta t is always positive. Okay, because we cannot go back in time, right? Delta t is always positive. Always positive. Delta x can be negative or positive.
Professor, I have a question.
Yeah, go ahead.
Can delta t be equal to 0 at any point?
Yeah, no, let's see. Can delta t be equal to 0? Yes, it can. If you have simultaneous events, yeah, like two lighthouses flickering simultaneously, the delta t between them is 0, right? Right? But you cannot have delta t equal to 0 for a single object. Okay? For this specific case of motion that we are studying, the motion of a single object, there is no delta t equal to 0 for the object. There is there is a limit in which delta t becomes smaller and smaller, but that's more for a more advanced course. Make sense? For simultaneous events in which you have two different objects, like for instance, two lighthouses, right? Synchronized, flickering at the same time, we can see that because they're synchronized, their delta t are equal to 0. Okay, but delta t equal to 0 applies just to to two objects, not just a single object. Okay, I don't need that anymore. Okay, and okay, here's another example, right? Here's another example of initial position of an object, final position of an object. In real life, object doesn't move uniformly. You can have a motion that goes slow and accelerate, goes slow and accelerate. But we're going to talk about that in the next idea that we're going. It's 9:45, right? So here you go. Tertiary definition. Here you go. Here's my tertiary definition. Now, in our specific case, we had, I'm gonna update that at this one here. Final position 7, initial position 4. Here you go. Final position 7, initial position 4. 7 seconds here. Is that 7 seconds? Wait a minute. No. Yeah, it's 0 and 3. Okay, it's not 7, it's 0 and 3. 7 was the position, right? 3 seconds and 0. Here you go. 3. Here we have, I'm going to emphasize this plus 3. And then what we got? We get this new, we get the average velocity, which by the way, has this new unit of meters per second. Remember that I mentioned to you, we can multiply and divide units, but we cannot sum and subtract different units. We can multiply and divide different units, okay? And that's how we abbreviate the unit for the velocity. We put it between square brackets. The unit of average velocity is the unit of delta x divided by delta t. And we can separate that unit of delta x divided by unit of delta t, meters per second. Okay, so let me write that down here. Although we cannot add and subtract different units, right? We can create new composite units by multiplying and dividing them. That's the case of the unit for the average velocity. Okay? In which we get meters per second. Meters per second. So 948 right now. Let's take our break. Break. Uh, 9:50 to 10:05 a.m. Okay. So if you don't have any questions, when you come back from the break, I'll take attendance, okay? And I'll see you in 15 minutes. Okay, let me take attendance. And okay, okay, that was a holiday. Okay, the same. September 12th. I'm gonna share my screen. Okay, Neil, Adino, are you there? Let's see, I'm looking here at my list. I don't see Neil and Nino here. Maria Argelis, are you there, Maria? Argelis Ramirez. I don't see Maria either. That's Jade Izquierda.
Here.
Okay, thank you. Vanessa Bonilla.
Here.
Thank you. Makin Levy. Curto. Okay. Thank you. Ashley Diaz. Okay. Michael. Ashley, are you there? I see Ashley here in the, make sure that you are in front of your computer when you call your name, otherwise I'm gonna put a star here. Fisher Dawn.
Yeah.
Okay. A Blessing.
Here.
Okay. Okay, Blessing, okay, and okay, good. Next is Lucy, Spitia, Roach, right? Lucy, I don't see Lucy here in my list. Next, Erika Fajardo.
I'm here.
Okay, thank you, Erika. Janet Garcia.
I'm here.
Okay. Makin, are you there, Makin? I see that you're. Yeah. Let's see. I'm gonna mute you, okay, Makin? Go. Raymond Garcia. Okay, good. So, okay, Raymond is here. Donovan Harris. Donovan, are you there? Okay, I don't see Donovan here. Okay, so we go. Oh, I'll get to you, Lily. Hang in there. Okay. Next, Lily. Okay, that's you, right,
Hi,
Lily?
Professor. Also, thank you for changing the syllabus. Thank you so much. I really
Okay.
appreciate it.
Oh yeah, that's right. I uploaded the new syllabus there, and just check it. It's version number 3. Next is Michael. Ashley.
Hi,
Okay.
Professor. I'm here.
Okay.
Professor, I'm
Oh,
here.
wait a minute. Let me. Who is that?
Michael.
Michael Hassid. Okay, good. Next,
Yes, thank you.
Wendy Hernandez.
I'm here.
Okay. Joshua Jimenez. No, I don't see Joshua here. Bethany.
Hello.
Okay, you're there. Good. Thank you, Bethany. Next, Sonny. I don't see Sonny here. Next one is Luis Fernandez Latiza.
I'm here.
Okay, thank you. Ana Gabriela Lopez. Good, thank you. Basilio Lopez. Good. Vahag Mard.
Here.
Thank you. Daisy Mariscal.
Here.
Good. Next, Alejandra Marmolejo.
I'm here.
Thank you. Amarilis Mejia. Okay, Amarilis, I don't hear from you. I'm gonna put a star here, but I see your name there in the list.
I'm here.
Okay, thank you. Julissa Molina. I don't see Julissa in my roster. Now, Yesenia Montes Rodriguez. Hi, Yesenia. Okay, I can't hear you, so I'm gonna put a star, but I see you in my list. Mary Okeki. Is Mary there? Okay, I can't hear you, Mary. I'm going to put a star here. Ryan Ong.
I'm here.
Okay, thank you, Ryan. Next is Artur Pacheco.
I'm here.
Next is Jennifer, thank you. Jennifer Perez.
I'm right
Professor
here.
Mary's here.
Okay, Mary, okay, Mary Okeke.
Yes,
And
Professor.
yeah, Jennifer.
Yes, I'm here.
Okay, thank you. Jennifer. Okay, next, Lady Lud. Are you there, Lady Lud? Okay, thank you. Lydia Rosas Buenrostro. Thank you, Lydia. Pedro Ruiz. I don't see Pedro in my list. Samuel Sanchez. I don't see Samuel either. Donia,
Here.
thank you. Elika Vafay, right? Lydia. Elika, I don't see Elika here either. Brianna Valencia.
I'm here.
Okay, thank you. Mia Villalobos.
I'm here, Professor.
Thank you. Next is Justena Youssef.
I'm here.
Okay, what about Arika Rice? I don't see my list. Was everybody called, by the way? If your name was not called, please let me know. 30. See one. We have 33 students participating, but I have only 30 here accounted for. Yesenia, are you there, Yesenia? Okay, so Kelly, okay. Yeah, okay, thank you. I'll add here your name, Kelly.
Thank you.
So is that anybody else who's trying to Bahara, Abujara, Kelly? Okay, so I will reply to you. So just bear with me, okay, Kelly? And good now. $31, $32. Anybody else was not called? Samuel, let's see. Sonny, are you there, Sonny? I don't see Sonny here. Joshua, are you there, Joshua? Nope, don't see Joshua either. Donovan. Okay, so let's proceed. And here's the syllabus, right? Okay, this is Monday, September 12th. We're doing 1D motion. Next time we're going to do our first lab. And let's proceed here. Okay. Yes, we have. Let's see. We have the syllabus there, Erica. By the way, I didn't upload the notes yet. Okay, so bear with me and remember me at the end of the class to upload the notes. So I didn't upload the notes yet, but I will be doing that at the end of this meeting. Okay. Okay, so here you go. Let's formula so far, right? The summary. What do you need to know? You need to know the basic quantity of time. We are using the basic quantity of time, or using the primary definition of position. And we use the primary definition of position to define displacement with the secondary definition, right? Secondary definition. And then from there, we use the definition of displacement plus the definition of time to define the average velocity, which we call a tertiary definition. And then we also have, another tertiary definition that we call the instantaneous velocity. It's possible to do that in physics, okay? How do we define the instantaneous velocity? We're not going to cover that here because that requires calculus, but I want you to know, okay? What's the instantaneous velocity? The instantaneous velocity is the average velocity taking a delta t going to 0, okay? So we make delta t very small. When we make delta t very small, delta x also becomes very small. Okay, when we divide this by the other one, we have what we call the instantaneous velocity. By the same token that we can visualize the average velocity in a graph, we can also visualize the instantaneous velocity in a graph as well. Okay, let me show you how. Okay, here you go. Here's the average velocity. You have already seen that, right? 2 points in the x versus t graph. The average velocity is the slope of this straight line connecting those 2 points. Okay. In real life, you are going to have more points in between this spot and this spot. That's what we have in real life. Okay. So in real life, if you were to plot the position versus time at a very small intervals of time, let's say you'd get something like that. Okay. So let's say the position varies with time, like this curve that you see right here, right? The object started at this initial position, right? It moves very fast to this point here, and then it slows down. How do I know it moves very fast and it slows down? Okay, I know it moves very fast and slows down because the slope between those 2 points is very steep. And I know that its velocity is very slow here because the slope in this region here is very shallow, right? The average slope between the average velocity between this point and this point is going to be the slope of this curve. But what about the instantaneous velocity? Let's say the instantaneous velocity is going to be given by the instantaneous slope at that point, the tangent at that point. Okay, that's what the instantaneous velocity is all about. If you want to know the instantaneous velocity at instant t equal to t2, what you have to do? You have to, I'm going to do the following. Here you go. If you want to know the instantaneous velocity at t1, at t2, or any other spot, okay, what you have to do, you have, to get the line that's tangent at this point, okay, right here. And that the line tangent at the point is going to, the slope of the line tangent at this point is going to be the instantaneous velocity. If I want to know the instantaneous velocity at this point also, right? If I want to know the instantaneous velocity at another point, what do? You take the tangent at that other spot and measure the slope of this line. Here too, it's the same thing. Here you go. Let me erase this one here. At this point, it's not tangent, right? It's going to be tangent. The tangent is going to be somewhat like that. Okay, it's a very slow It's a very shallow slope. So I need you to practice that. Let's write that down in the notes. Not this one here, this one right here. Okay. The unit of instantaneous velocity is also the meters per second, right? And here we go. In order to calculate the instantaneous velocity, comma, you need calculus. Okay? Another way of finding out the instantaneous velocity is by plotting x versus t, right? For, for intervals of time that, for intervals of time that are very close to each other, and finding and determine, right? Determine the slope of the not the slope, the tangent. Yeah, the slope of the tangent, right? Slope of the tangent at a specific point in the graph. Okay. I'm going to give you a very simple example. Okay, the simplest example that you're going to see out there of a tangent. Let's see, here you go. I'm going to give you another example. Here you go. Take this one out. I don't want this one here. We have the case of graphs. Okay. Oh, that's V. Wait a minute. That's, oh, I want X. Yeah, I want X here. Here you go. I want to erase this guy here. Okay. X versus V versus T. The simplest type of motion that they're going to see out there is the type of motion that we call uniform motion. In the case of uniform motion, the graph is just a straight line. The graph of X versus T is just a straight line like that. Okay. So now I ask you, what's the slope of this graph at this point? What's the slope compared to the slope of this graph at this point, right? So if you have if the object is moving, if there is a linear relationship between X and T, the slope along this line is going to be the same. That's the simplest type of motion that you're going to see out there. Okay. The slope here is going to be the same as the slope here. Okay. For the case, here you go. Let's write that down here. For the case of uniform motion, okay, which is defined as motion with constant velocity, comma, the X versus T graph is a straight line. Recall that a straight line has a single slope, has the same slope everywhere. Okay. So the slope of the line coincides with the instantaneous velocity in this case, okay? But then we have other types of motion as well. We can have types of motion that's going to look just like that, like a parabola. Let me get this one here. Okay. Can look like we can have this type of motion here. Okay. In this specific case, okay, I'm going to go even further than that. Here you go. I'm going to make this like that. Okay. In this specific case, the instantaneous velocity at this point right in here is going to be the slope of the tangent, of this tangent to the graph. Okay. At another place, let's say right here at the peak, right at the tip of this graph, the instantaneous velocity is going to be 0. Do you see that? Here we have a positive velocity, positive instantaneous velocity, because the slope is positive. Here we have a 0 instantaneous velocity because the slope is 0. And then you should, on the other side of this graph, we are going to have a negative slope, which means that the instantaneous velocity is negative. And what means negative velocity? Negative velocity means negative displacement. Negative displacement means that the object is moving, in the direction contrary to the direction of the axis here. It means that the object is moving, downwards here in this graph, right? That's what it means. Okay, so for the case of non-uniform motion, okay, we can have different types of instantaneous velocities depending on the instant of time. In the example shown in the PowerPoint slide, okay, the object initially has a positive instantaneous velocity, comma, it comes momentarily at rest, and then continues moving along the negative direction of the x-axis, okay? So I'm gonna illustrate for you in PowerPoint again what's happening to this object, okay? So you can visualize it better. This graph here, what this graph is telling us, okay? I'm going to show you a movie, how the object is moving in this case. I'm gonna need, just like we had before, I'm going to need an x-axis, right? Here you go, and the object. I'm gonna copy that here and paste. If I were to run a movie for this graph here that you see, okay, our object would start, our particle would start somewhere around here, nearby the origin of the x-axis, okay? And with a given velocity, and little by little it should slow down. That's what that graph means, okay? It should slow down, coming to a moment, to an instantaneous rest, and then moving backwards at ever increasing speed. That's what that graph means. That's what this graph here means. I'm going to put that dashed, dashed, and dashed. Here you go. Yeah, here you go. Just to illustrate the slope. Okay? So two different ways of describing the motion of a particle. With a graph, x versus t, or with a movie, right? Showing this particle moving along this x-axis. Let's see, I'm gonna do that for you. Here you go. Initially like that, and then it moves a big distance, right? Right in here. Then move just a little bit less than before. Okay, a little bit less, a little bit smaller displacement, right? And then momentarily at rest, and then it start to move in the other direction. Maybe I'm gonna copy here. This one right in here, right? Momentarily at rest. This one here, 1, 2, 1, 2, 3. Let's see if it's working. We start, here you go. We start right in here, big displacement here, smaller displacement here, even a smaller displacement here, almost instantaneous at rest. You start to move to the other direction, in the negative direction. Oh, not this one. Let's see. Yeah, not this one either. Here you go. I want this one here. I want to plot. Here you go. This and this. Now we can play the movie. That's what the graph means. You know, that's what this graph means. Very fast initially, slows down, come to an instantaneous stop, and start moving the other direction. Okay? That's what that graph means. Can you picture that? Okay. Okay, so here is our summary of formulas. Start with the position, then we go to the displacement, we define average velocity, and then we define instantaneous velocity. You have to know how to interpret the graphs, okay? You have to know how to plot the position of the particle versus time, okay? To know how to plot the position of the particle versus time. You have to know how to interpret the average velocity from the x versus t graph, okay? The slope of the straight line connecting the 2 points in the graph. You have to know how to interpret the instantaneous velocity from the x versus t graph. Okay, I don't want to do this one. Okay, here you go. Here are illustrations of what we mentioned. Okay, instantaneous velocity is going to be the slope of the tangent of the line tangent to that specific point. I'm going to write that down here. Here you go. You have to know how to interpret instantaneous velocity from the x versus t. Slope is slope of the, not the straight line, the slope of the tangent of the line at the point where the instantaneous velocity, where you want to find the instantaneous velocity. All right. Okay, what else? 1038. We are going, let me erase that. What else we have in addition to displacement, average velocity, and average, in addition to position, displacement, average velocity, and instantaneous velocity. Instantaneous velocity. We also have distance traveled d and speed s. Okay, which are always positive quantities. Make a note that distance d is different from displacement. Distance d is different from displacement and position. Speed too. Speed s as well is different from average velocity and instantaneous velocity. Okay. These two quantities are always positive, whereas position, displacement, average velocity, and instantaneous velocity can be either positive or negative. Okay, so what's this thing about this distance traveled? Okay, we can put right, yeah, distance traveled. Well, distance traveled d is not, distance traveled d is nothing but what the odometer of your car displays. Okay, distance traveled d is nothing but what the odometer of your car, display. Okay, it doesn't show anything negative there, right? The odometer of your car is always positive. That's what distance traveled is all about. Displacement can be positive or negative, can be zero. So here you go. I'm going to give you another example here of distance traveled. Okay, here you go. Going back to this video right in here. Okay, this particle is moving from this position to this other one here. Okay, here you go. This distance here that you see, this, in this specific case, the distance traveled by this particle coincides with the displacement. Okay, in this specific case, from this point to this point. We have the same thing here. The distance traveled from this point to this point coincides with the displacement, not with the position, right? The position is different. When does the distance traveled becomes different from the displacement? Okay, when does the distance traveled becomes different from the displacement? Okay, so let's continue here with our graph. Okay, from here to here you have a larger distance, right? Again, from here to here you have a larger distance as well. Both distances and displacement in this case, from here to this last point, they end up being equal. Now things start to change when this particle changes direction. Okay, so we're gonna get this particle to move to that position. What's going on here? Let's see here. Here you go, right in here. Distance travel from here to here is going to be positive, but not the displacement. Okay, let's go again. Here you go. The displacement from that point to this one right in here is going to be what? It's going to be 0, because the final position coincides with the initial position. Okay, let's do that again. Here you go. It's like what you see right in here is like the particle moving from this spot to this other spot here, right? At this instant of time, the position is, let's say, x naught. At this other instant of time, the position also is x naught. The displacement is 0, because the position is the same, but not the distance. The distance is going to be what? It's going to be this distance traveled plus this other distance traveled. So that's the difference between distance and displacement. Okay? Any questions about that? Remember that. And speed, what's the speed? The speed is always going to be, you know, speed is always going to be positive. Speed. Okay, how do we calculate the speed? Calculating the displacement is rather challenging. Okay, it's not easy to calculate the displacement in general. Displacement calculation is easy to do in one dimension motion only, but when it gets to, you know, to two-dimensional motion, three-dimensional motion, becomes very difficult to calculate the displacement. Unless, so it's easier to measure, right? Like in the case of odometer, but the calculation is more difficult. Now, what about speed? Is speed, okay? That is average speed and instantaneous speed. Instantaneous speed, okay? And the speed s will always be the positive value of whatever velocity we are working on. Okay, so that's what we have. You go, distance is what the odometer of your car indicates. Your odometer of your car does not indicate position or displacement. Mathematically speaking, that's how we define distance traveled in a single direction for the one-dimensional case, right? In a single direction. If you change the direction, then we cannot define that mathematically. Distance is always positive and can be greater or equal than displacement, depending on the situation. Velocity can be either positive or negative. You know, average speed is going to be the distance traveled divided by delta t. Okay, in the one dimension, oh, that's how we define average speed, okay? Is the distance traveled by delta t. Remember, average velocity, right? Go. Average velocity is delta x over delta t. Average velocity is going to be, you know, delta x over delta t. And can be either positive or negative, but average speed is d over delta t. Okay, for one decade and a particle traveling in a single direction, the mathematical definition of average speed is, you know, the magnitude of the average velocity, but only for one-dimensional case. But in general, it's always going to be greater or equal than the average velocity. Okay, so 47. We have let's see if we can come up with a little quiz now. Okay. Any questions before we move forward? Okay, so I'm gonna give you a quiz before the end of this class meeting. Okay, so make sure you are there. Do you access to? Yeah, you're gonna have access to. Let me pay. Yeah, good point, Basilio. Let me save it right now, so you can have access. Keep in mind that I am changing these notes on the fly. Okay, those are old notes that I had for another course, so I'll be updating these notes for you folks. And just keep that in mind, okay? Notice that if you go here on the dates, those were my notes for, see here the date, 2021, February 2021, right? For a previous course that I taught. So as we go along the semester, I'll be updating those notes, okay? And save as, I'm going to save as a PDF file for you. PDF. And I'm going to upload it right now. Let's see, college for lecture notes. Is that the one? Huh. It didn't save it. Let's try it again. Yeah, that's right. I didn't fix it yet. I tried to fix today, and for some reason, Canvas didn't fix it by itself. Okay, I gotta call the people that are at Canvas to see what's going on. Okay, looks like we have some bugs in Canvas. That's why the grade was not fixed. Okay, so hang in there, bear with me, and I'll get that fixed for you. Okay, so finally we get it. Okay, here you go. Yeah, I got it. I'm gonna upload this note. Okay. So as we go along on the fly, I will post in there. You will be able to see what's gonna come next, but there will be some modifications, okay? Because I'm always changing it on the fly as I lecture you. So we'll get here, folder, physics 6 group folder, shareable folder. Okay. Here you go. So the notes is right in there. Let's see. I think we can go in a break right now. 11, let's see. Yeah, okay, let's have a break right now. It's 10, almost 10:55. Otherwise we get burned out, right? Let's break till 11:05. Have you noticed that when you work too hard, you start to feel that you're not being very productive? You know, it's always good to take a break every hour or so. You know, that's what I have found out. Give it some time to cool down the brain, right? The brain is a machine that consumes lots of energy, by the way, and it needs rest every hour or so. So break till 11:05 is 10:50. Let's see, 10:55. No, 11:10, right? 11:10. Now, average. Summary. Okay. Break till 11:10 a.m. If you don't have any questions, I see you in 15 minutes. Okay. Okay, were you able to access my notes there in the Google Drive? Okay, good. Okay, that's good. So let me get that. Someone is asking for the link. Okay, someone else did that for me, right? Thank you, Bethany. Okay, so let's do a quick quiz, right? So we can change our quiz 4. Okay, I'm going to bear with me here while I prepare this little quiz. It's 11:13 right now. Okay, we have 45 minutes of class, right? One is that. Let's okay. Mm. No. Wait, X versus T. Oh, okay. Is with 6. And okay. And this. The information provided. Instantly. It is. I will see. This is information. Average velocity.
Professor, do we start the quiz or um
Hang in
Wait.
there. I'm preparing the quiz. Hang in there. Instantaneous. I'll be getting back to you very soon. Instantaneous.
Thank you.
These are okay. Okay, so here you go. I prepared here. the first quiz, the quiz number 4, right? Like I said, quiz number 3, I tried to fix that problem. I couldn't. I have to check with the people at Canvas what's happening there. In the past, I was able to fix that for other exams, but this time, I couldn't. But I'll get to it. Just hanging there. Okay. Now, quiz number 4 is 11:20. Let me start sharing the screen here. I'll let you think about that while I share the screen. Here you go. Quiz number 4. Okay. Now I'm going to let x be 4 meters and t equal to 1 second. What's x plus t? Okay. So you have all those 4 options. Let's see if I can do something else. Yeah, here you go. I'm gonna do it like that. And then I'm gonna give you some time to think about it, and then I will give you the opportunity to answer your question. Quiz number 4.
Professor, do we start the quiz on Canvas?
Oh, I'm getting ready for you. Okay,
Oh,
hang it
okay.
there. Okay, I'm time limit to now. Today is, let's see. Okay, now you can do quiz number 4. Let's see here. Okay, quiz number 4 is available for you to do. Let me know if you have any problems accessing. Quiz number 4. Okay, so let's see. Interesting. Why it's not? Okay. Let's see. Okay. Are you done with quiz number 4? Okay. And you must have quiz number. Okay, quiz number 6. Let's see how you quiz number 6. Okay. Two. 40. Huh. Interesting. Okay. No, two. Okay, available. Okay. Huh. Interesting. Now let's see each one, each of the quizzes here. Okay. Are you having anybody's having any problem accessing the quiz number 4 question? Let me check here. Let me see. Let me do some moderation and see what's going on. Okay. Yeah, most of you did it. Okay. And now no problem, right? Now let's see. Let's go for quiz number 5. Quiz number 5 is going to be due at 11:35. Let's see, everything is fine here. Available. What time is available? Available 11. Okay. So we still have good. So, okay. Everybody's done this quiz number 4. Yes. Let's go for quiz number 5. Okay, choose the correct answer. Do you see here quiz number 5 is 1 question per quiz, right? Choose the correct answer. Displacement is always equal to distance traveled in a x versus t graph. A positive instantaneous velocity is depicted by a tangent line with a positive slope. And then you have these other options in a x versus t graph, a negative instantaneous velocity depicted by a tangent line with a positive slope, right? See, negative, positive, negative, right? And in a x versus t graph, a positive instantaneous velocity is depicted by a tangent line with a slope equal to 0, with a slope equal to 0. Equal to 0, okay? So you have everything that you need to do this quiz number 5. Do you still see the questions, by the way? Here in my screen, I'm sharing the screen with you. I want to make sure that you still see question, the question for quiz number 5. Can I hear from you? Okay, good. Thank you, Basilio.
Yes.
Okay, thank you. This one is due 11:35. Right. Oh gosh, why you keep on doing that? Interesting.
Professor,
Yeah.
I have a question, but I don't want it to give, there's a possibility that it gives away the answer to the quiz
Okay.
question.
Send me a chat, a private chat message. A message to the private chat so nobody else can see it, please. That's quiz number 5. Are you done with quiz number 5? Let's see, at 11 you have. Okay. Okay. Are you done? So let's see, 11:33, right? Okay. Okay, I will talk about that, Makin. So let's see, let's go for quiz number 6. Okay, 11:33, right? And let x be 3 meters and t be 4 seconds. What can you tell me about the instantaneous and average velocities? Okay. Option A, neither velocities can be calculated with the information provided. Instantaneous velocity is 0.75 meters per second. Average velocity cannot be calculated with the information provided. Average velocity is 0.75 meters per second. Instantaneous velocity cannot be calculated with the information provided. Both average instantaneous velocities are 0.75 meters per second. Which one is the correct alternative? Okay. Let me take a look here. Okay. Okay. 4, 5, and 6. Okay. Two more minutes to go, right? Let's see how you are all doing on that. Yeah, most of you did well in the first one, and the quiz number 4. Yes, Blessing. Yes, like I mentioned at the beginning of the class, Blessing, I'm trying to correct quiz 3. Okay, I'm trying to correct the problem with quiz 3. I tried this morning, it didn't work out. Something wrong with the software there in Canvas. I will try to fix that soon. So bear with me, okay? And I'll get it right. Let's see. Now, quizzes. Last one, 11:37. One more minute to go. Okay, we're done. We're done with quiz number 6. Let's see how we did with quiz number 5. Yeah, let's see. Okay. Yeah, most of you did well on the quiz number 5 as well. Let's see quiz number 6. Quiz number 6. Okay. Yeah, quiz number 6 was more difficult, huh? Okay, so let's talk about those questions. Okay. Okay, quiz number 4, right? 1140. X equal to 4 meters, t equal to 1 second. What's x plus t? Okay. Can you sum x with t? They have different units. Can we sum x with t, right? Okay, just like I mentioned at the beginning, right? Quantities that have different units cannot be summed nor subtracted. They can only be divided or multiplied, okay? So the correct answer should be D. That would be the correct one. Okay. I understand some of you got it, right? Some of you didn't. Most of you got this answer correctly. Let's see, yep. Make sense? My quiz 3, yeah. Now, next one, choose the correct answer, right? Displacement is always equal to distance traveled. Is that correct or not? Okay. Well, sometimes displacement is equal, but not all the time. Okay, so this one, because we have I put always there, that doesn't apply. That shouldn't apply. Okay. And then we have the cases of x versus t graphs, right? So I covered that in the x versus t graph, right? You can have all sorts of x versus t graph for instantaneous velocity. Okay, so here you go. Here is one possible. Oh, let me now share the. Let me share the screen. Okay, here is one possible x versus t graph. Okay, here is one possible x versus t graph. You have an instantaneous velocity here. You have another instantaneous velocity here. You have another instantaneous velocity here. You know. And here the instantaneous velocity is positive. Up to here, the instantaneous velocity is positive. Past here, the instantaneous velocity is negative. Note that in this specific example, the instantaneous velocity is changing as time goes by. Okay, that's one type of motion, like I mentioned there in the lecture today. Here is another type of motion. Here's another type of motion in which the instantaneous velocity is constant. Okay, so depending on the type of motion, the instantaneous velocity may or may not be constant. Okay, in this specific case, the instantaneous velocity is constant because there is a linear relationship between x, between the position and time. Okay, so that's here you go. I'm going to show you here. Here's another example of an x versus t graph, far more complicated than the other, right? Let me see. Here you go. Okay, here you go. The part x versus t is far more complicated than the other two, right? Here's the picture of instantaneous velocity. This instantaneous velocity has a shallow slope. And here's the depiction of another. Here you go. I'm going to depict another case of instantaneous velocity here. I'm going to get a line that's tangent to this curve right in here. The slope of this tangent line is equal to the instantaneous velocity. So instantaneous velocity may not be necessarily the same all the time. No, it all depends on the graph that I gave to you. Okay, in this case, instantaneous velocity doesn't change. In this case, instantaneous velocity is the same. In this case, instantaneous velocity changes as well. Okay, so let's go back to our, is that clear? Someone was asking me that. Okay, all depends, you know, it all depends what type of motion we are referring to. So let's go back to my quizzes right in here. Choose the correct answer. Displacement is always equal to the distance traveled. No, it's not always. Sometimes it's equal, but most of the time it's not. In an x versus t graph, a positive instantaneous velocity is depicted by a tangent line with a positive slope. Yeah, positive slope. That's the right answer. Oops, that's the right answer. Okay. Positive slope of the tangent line means positive instantaneous velocity for x versus t graph. The other two are incorrect. Okay. That's quiz number 5. Okay. And then quiz number 6. Let's see here. Let x be 3 meters and t be 4 seconds. What can you tell me about the instantaneous and average velocities in this case? Okay. Okay, so in order to solve this problem, you have to go back to the definition of instantaneous and average velocities, right? Mathematical definition of instantaneous and average velocity. I'm going to write that down here just to remind you. What all you need is the average velocity. Didn't do it. Let me get this equation elsewhere. Right in here. Okay. Average velocity is what? Is delta x over delta t. Okay. Here you go. Okay. Note that you are required to have this information, delta x and delta t. Did I provide you with delta x here in the formulation of the problem? You gotta ask yourself, okay? And what is delta x and what is delta t, right? Delta x is what? Is final position minus initial position, right? Do you have final position and initial position there? Did I give you final position and initial position there in the formulation of the problem? I didn't, right? No, right? So because I didn't give you delta x nor delta t, but only a single value for position and a single value for the instant of time, you cannot solve this problem. You don't have enough information. You cannot calculate neither the average velocity and nor the average velocity, neither the instantaneous velocity. Okay? Especially the instantaneous velocity, that's far more difficult to calculate. So everything else should be incorrect. You do not divide one by another one. But if I had given you, if I had given you, let delta x equal to 3 meters and delta t equal to 4 seconds, yeah, you could, the answer would be different, right? So variation, right? A variation of this question, right? Suppose that instead, right? Suppose that instead, 6 prime, instead I have told you, right? Let delta x equal to 3 meters and delta t equal to 4 seconds. What can you tell me about the instantaneous and average velocities, right? Well, in this case, the correct answer would be this one. I made just a minor change to the formulation of the problem, and I'm getting a different answer, okay? Make sense?
I'm still a little confused here.
What?
I'm still a little confused here. For question 6.
Yeah.
So you had described it to us as something that could either be calculated with using a form of calculus, or something else. 1 second here.
Yeah.
Sorry, give me 1 second.
To calculate the instantaneous velocity, you need calculus, right? But you still can have an idea of the instantaneous velocity if you have a graph of x versus t, right? But don't forget, the instantaneous velocity is still a function of delta x, right? It's still a function of delta x. The instantaneous velocity is what? We go instantaneous velocity v. Okay. V is what? The limit. Well, let's see how I can do that. Limit right in here. Limit, yeah, here you go. Limit of delta t going to 0. Average, right in here. Is that clear? Average, okay, here you go. Like that. Note, see that the instantaneous velocity still requires the information for delta x, right? Any questions?
Professor, can you scroll up to quiz 6 again? I was writing the formula. Can
This one
you
here?
scroll? Let me scroll down. I'm sorry.
No? Okay. So it's Cannot. Go. Okay, what time is that? Any more questions? We're almost running out of time here, right? 11:51. Let's take advantage of those 10 minutes left. Okay, and okay, 8 more minutes left. Any more questions? Can we move forward? Yeah. So why are we doing that? We're doing that because would you add? There's nothing Canvas. Let's see. I already uploaded the notes to the Google Drive. Okay, Wendy. So you can look at the notes there. You can look at the notes there. Everybody was able to download the notes in my Google Drive, right? Okay. Okay, good. Now, here you go. That's what we're going to do next. What are we going to do next? Okay. We're going to, based on those definitions of average velocity, instantaneous velocity, we are now going to study some types of important types of motion. Okay. Again, it's still one-dimensional motion. And the first type of motion that you're going to study is that of a particle subjected to constant velocity. Okay, constant velocity, that's also called uniform motion. Uniform motion is that if the velocity is constant, you have uniform motion. That's still 1D, one-dimensional motion. That's how we abbreviate this case, the constant, the fact that we have constant velocity, we write down V equal to constant. Okay. And by V, I mean the instantaneous velocity is constant. We do have this type of motion. I'm going to give you an example. Examples of uniform motion. Of 1D uniform motion. Okay. A car set with a given speed, a car moving, right? Moving in a straight line in the freeway at constant speed. That's an example of uniform motion in a straight line in the freeway at constant speed. That's one type of example. Another example, if you ever a skydiver who has reached terminal speed, has reached terminal speed after, dive from a plane. He didn't open the chute yet. He did not open the chute yet. Parachute yet. Chute, right? He didn't open his parachute yet. That's another example. The skydiver, let's see. Not from a plane, it would be better from a balloon, from a stationary balloon, okay? Stationary balloon. the airplane can be moved in the horizontal direction. So that wouldn't be exactly an example of 1D uniform motion. If you're familiar with this type of motion, you know, if you're a skydiver, you jump from a stationary balloon at a very high altitude. Okay, as the skydiver keep on descending, he's gonna encounter more and more air resistance. Okay, he's not changing his position, he's just, you know, falling with his head, his arms straight. Eventually, it comes to a point that his speed is high enough, so the air friction is also high enough to counter his weight, and then he starts descending with constant velocity. That's one example of another example of on the uniform motion. Okay, so how do we move about getting what I call the equations of motion? Okay, the equations of motion is nothing but, you know, a relation between the position and the velocity. Okay, so we start, you know, we start with the equation here for the average velocity, delta x over delta t. Because the velocity is constant throughout the motion, the average velocity also coincides with the instantaneous velocity. Okay, so here you go. That's how we do it. That's a better way of formulating the solution of this problem. Okay, average velocity is delta x over delta t, but the velocity is constant. Consequently, the average velocity is equal to the instantaneous velocity, and the instantaneous velocity is also equal to delta x over delta t, which is xf minus x naught. I'm going to go another step. We usually drop the f subscript to make things simpler. Okay, and we can here write like that. Now, t naught is also usually chosen as being 0 seconds. I'm going to write it down here. X naught doesn't have to be necessarily 0. You can start your motion at a different spot other than the origin of your axis. Okay, and now we have this relation for the instantaneous velocity and delta x over delta t, something like that. Okay. What do we want to do? We want to write x in terms of the other parameters that you see right in here. Okay, so this one belongs right in here. Oh no, not here. This one belongs right in here. Okay, to 0. And now we solve for x. Just like, let's see here. I'm gonna do for this one here, we're gonna pass the t to the other side. This is algebra, right? This is regular algebra that you learned in your math course. And x. Okay, like that. So for x, and we have what we call our first equation of motion. Okay, which is nothing as x written as a function of t. And we represent that like that. X as a function of t, which ends up, and this function of t ends up being a linear equation. So it's 12 o'clock right now. And I can erase that. Here you go, to simplify our notation. This one belongs right in here. Okay, go to 0. Here you go, to simplify our notation, we eliminate the f subscript. We can name our parameters. Okay, and that's what we have for uniform motion. We're going to elaborate a little bit more next time. Any questions? Okay. Okay, so
Professor,
Yeah.
Professor, for the quiz, one of the quizzes I just did. I mean, I turned it in on time, but it says late. I don't know why. Maybe because of my Wi-Fi. But I got a good score. Does it matter if it says late on the quiz?
Who is that? I don't. Let's see. What's her name?
This is
Oh, it's
Lily.
Lily. Well, Lily, I don't know what to do. Okay, it's oh, we can talk about that later. Let's see exactly what happened there. I do not know what happened there. So okay, just remember that you have 3 minutes to do the quiz, right? And
Yeah.
most likely you started at the time and you know before the quiz was due. But don't forget there's 3 minutes for the quiz, right? If you start 2 minutes, there's 3 minutes for the quiz that I schedule for you, and on the top of that there is a due date as well, right? If you start the quiz 2 minutes before the due date, you don't get all the 3 minutes, right? Okay, so maybe that.
Okay.
Okay, maybe that's what happened. Okay. So anybody else? Okay, so let's stop sharing the screen here. Okay, so we have office hours right now. If you want to stay around to ask any questions, I'll be available. I'll be available until 1:05 for another hour.
Professor, I had one question.
Yeah, who is that?
Donia,
Donia. Okay. Hi, how are you doing?
good. How are you?
Okay.
I noticed that we had one homework assignment that was due, that has the due date of December.
Uh-huh.
We're gonna have more, or are you gonna upload more homework assignments?
Yeah, I'm
Or
going
is
to upload more. Yeah, I will. Hang in
Alright.
there. I don't want to overwhelm you all, right?
No, yeah, I was just curious just because the due date was so far ahead, so I didn't know
Yeah,
if.
yeah, I like to give you as much time as you can to finish the homework. Okay, so basically, but if at the end of the semester you still need more time, I'm not gonna know, right? I give you, you know, I usually give my homeworks, the deadline of my homework at the end of the semester. That I usually do. Okay.
Got it. Thank you so much.
Okay, so. Are you still there, Kelly?
Yes.
Okay, good. So let me check what's the situation here. So let me see. Arika didn't come. Okay, you missed the last week, right? No. Okay, so let me check one thing here. 0. Okay. Let's see. I am at a point. Let me see if I have enough room there for you. Oh yeah, there's more here. Okay. It looks like attendance. Let's see. Yep. Okay, Sunny. Okay. Oh, see. And then some more sections. Yeah, okay, so let me see. Looks like I have room here for you. 1, 2, 4, 5. Let me. Are you still there, Kelly?
Yes.
Okay. Anybody else is around? Let me go to my roster. So you need an ad code, right?
Yeah, I do.
Let's see here. Okay, yeah, some students have dropped, so I can give you an ad code. Okay.
Oh, thank you, Professor.
Yeah, okay, so there is some room here. I'll send your permission, it's called permission number, right? Not ad code, but permission number. So I'm gonna send that through chat.
Okay.
Right? Through Zoom chat. Kelly. That's your permission number.
Okay, I got it. Thank you.
Yeah, hopefully you can add it right away.
Okay, thank you so much, Professor.
Welcome. Do we need anything? Blessing and Louise? Hmm. Okay, let's speak here. Molina. Okay. Really, about the money. Okay. Luis Pedro Ruiz. Oh, there's Ruiz is in the position. And Samuel Sanchez. Elsa? Okay, so